Welcome everyone. It's our usual Thursday seminar series, and we're delighted to have Joan here from Edinburgh. It would be wonderful to have Joan here as in person, but of course we'll have to settle for the virtual version. And he will be talking to us today about the JT mode in near-extremal Kerr. Joan, the floor is yours.
Yeah, thank you very much, Jeff. Thanks for the invitation. And you know, I would also like to stress, as I believe Jeff already knows, that I love your country, and it's a pity that I cannot be there. But let's hope that things will get better as soon as possible, whatever that means. And as we were saying before the start of the talk, please, feel free to interrupt me. If there are questions in the chat, please let me know, because I may not be able to realize this, but otherwise just jump in at any time, please. So indeed, let's see. Oh, now, yes, okay. So what I would like to talk about today, a little bit as to make sure that at least I convey the message to begin with, is the fact that typically there is a theorem in general relativity saying that, or in more gravitational theories, saying that near-extremal black holes have a geometry very close to their horizon, which is what technically people calls the near-horizon geometry. Those near-horizon geometries typically have ADS2 throats. This is a theorem in general relativity. And we've learned recently, thanks to the work of some people that I will review in a few minutes, that the low energy dynamics of these near-extremal black holes is controlled by some Goldstone modes. And the effective action is the so-called these days the Schwarzian theory, whose equations of motion are coming from some two-dimensional effective theory of gravity, which is called the Jacques-Tate-Bohm equations of motion. Now, we believe that story is general. What I mean by general is that it applies typically to any near-extremal black hole. And indeed, as I say here, it's in quotation marks why, once the masters have told you what the answer is, it's easy to show that, for instance, for spherically symmetric cases like Reisner-Nostrom black holes, you can show that these JT equations are there. And I will review it in a few minutes in BTZ, because I think that it's a nice story that will allow us to revisit what that means in ADS-CFT. But the main question today, eventually, that's why I want to make sure that I say this very early on, is, and as the title may have suggested, I'm literally interested in, well, I do believe that this Schwarzian theory should control the very low energy dynamics in the four-dimensional extremal Kerr, no string theory, no nothing. But the problem in near-extremal Kerr is that the spherical symmetry is broken. And so technically, it was not obvious to us how to identify the GT mode. So this Goldstone mode, sorry, I will refer to it as GT mode. So what I would like to eventually, it's a relatively technical discussion that I would like to have. That's the main question that I would like to answer before the end of my talk. Now, what I thought I would do is, there will be two main parts in the talk, and please, Jeff, Jonathan, if you feel that I'm going over some of the review in too much detail, which I hope it's not the case, please ask me to accelerate. This is mainly for young people, just to make sure that this is also useful for them. So I'm planning to review a little bit some of these early statements that I had in the previous slide. And then in the second part of the talk, I will basically describe to you what is the strategy that we followed in order to answer this question. There is an issue that when one discusses perturbations of near-extremal Kerr, one uses the Tchaikovsky formulation. This is a gauge invariant formulation, whereas the JT perturbations are typically in some written gauge. So there are some issues to sort out there. And once we identify the modes, I will also make some technical remarks about how to glue these modes as perturbations of the full Kerr solution. I don't claim to understand everything I would like to know about this gluing, but I'll let you know. I'll mention some of the features that I find more interesting. Okay, so if you are as old as I am, let me put it this way, near-extremal black holes and near horizon geometries, ADS2 throats, the relation to statistical mechanics, the meaning of ADS2 holography has been in the field for many years. It has appeared in different formalisms, Kerr CFT, of course ADS CFT, sense formulation of ADS2 entropy and higher order corrections. So there is a bubble of topics that this talk in one way or another could have some overlap, and that's a little bit the motivation for giving a little bit my own perspective, even though I'm not gonna say anything new, but I will be trying to make some comments about how the recent years have developed. So for someone like me, and again, thinking in terms of young people, I always like to start with relatively very minor remarks, but just to highlight that sometimes just by doing, oh, I hope that my internet survives. So let's consider the partition function of a quantum statistical mechanical model. For simplicity, I focus in a partition function that depends on two chemical potentials. Beta is 1/T, so it's the inverse of the temperature in some units. And let's pretend that dj is the angular momentum, because that's what I will be discussing in the Kerr discussion. And there is this angular velocity or chemical potential. Now, what I mean by extremal limit is taking the temperature to 0, which means taking beta to infinity. Now, if you want your statistical mechanical system to have some non-trivial structure in this limit, notice that when beta goes to infinity, this exponentially basically kills everything, unless the coefficient in parentheses vanishes. That's typically what happens, for instance, in supersymmetric situations, for those of you that may have encountered this, but supersymmetry is not required in this business. So in order to achieve this, typically what happens is that the angular velocity, so the second parameter in your statistical mechanical model, hits some bound value, in this case -1, say. And then in order to achieve some non-trivial, to keep some non-trivial physics in this limit, you need the two quantum numbers labeling your states, in this case the energy and the angular momentum, to be related. And in the example that I've written here, this would mean E equals J. So the intuition that you should have is that, just from this very simple consideration, is that if I am interested in studying near-extremal physics, you are typically going to be asking questions about what I would say near-extremal excitations. And one way of parameterizing this is in terms of this blue delta E, which basically tells you how far away you are from the extremal set of states where E is equal to J. So there is a small parameter in the game where this delta E is much smaller than J. So that basically comes almost for free from these statistical mechanical considerations. Now, I would like to relate these very simple observations. We know that the statistical mechanics is captured by black hole equilibrium physics. So I would like to rederive or to connect these observations about the near-extremal energy in terms of black holes and near horizons. For that purpose, I've written down here, this is not a general argument, so I apologize, but I hope that it's enough to provide this mild intuition about what's going to happen. Let's write down, let's focus on a two-dimensional slice on the metric of a black hole. I'm typically having in mind Kerr here. So this is the metric. This is supposed to be the S square, sorry. This is the line element of my black hole. I'm showing you the dt square and the dr square. And then you can see the function that determines the location of the event horizon. In a situation in which you have two conserved charges, such as the energy and the angular momentum in the statistical mechanical consideration, you will typically have two zeros here, the so-called inner horizon, which is r minus, and the outer horizon, which is r plus. Now, the previous near-extremal limit means taking t to 0, and in gravity, taking t to 0 means that these two roots, r minus and r plus, tend to be very close to each other. Now, the parameter beta in gravity is written by this red formula, and as you may know, the easiest way to derive this formula is by using the Hawking-Gibbons kind of trick, if you want to call it trick, and requiring the regularity of this metric in the Euclidean continuation when you go to an Euclidean signature. Now, bear with me and have this formula in mind. Now, the connection with near-extremal excitations and near horizon is the following. If I go to the previous metric, which is written in terms of T and R, and I consider the following large diffeo, and I insist with the word large, this is a change of coordinates, but it doesn't vanish at infinity, so it can carry physics. So if I relate my time clock to a new time clock T tilde by 1 over lambda, and I relate my angular momentum generator phi with a new phi variable, which is co-rotating because of this shift. If you think in terms of the Killing vectors generating you conserved charges, in gravity is more complicated, but it typically gives you a good intuition. Just using the chain rule in this change of coordinates, what you will learn is that the angular momentum measured by phi tilde and phi is the same one. But due to this shift between phi and t, the energy measured by partial t tilde is equal to the previous j plus some extra shift that depends on lambda. So coming back to our previous discussion, this is a change of variables so far that has the property that if I would be interested in analyzing energies which are very close to j, it suggests to take the lambda going to 0 limit because of this observation here. Now, the remark is that if I take lambda to 0 in this otherwise arbitrary change of coordinates, what I mean by arbitrary is that it's valid for any value of lambda. If I take the perspective of an observer at infinity, which is the one that sees thermodynamical equilibrium satisfied by your black hole, in terms of the time clock, it will require a long time to measure any physics near the horizon. So that observation is also captured by lambda going to 0. And finally, the way to connect this with the near horizon limit is that if I go to my previous metric, I'm telling you how t scales with lambda. I'm telling you how the angular variables scale with lambda. I need to tell you how to scale R. And indeed, people in GR like Gerok and Lucetti and many other people would tell us that the natural limit to take is to complete this large diffeo, but by defining R to be the outer horizon plus some correction, some small correction because it depends on lambda, and then some new radial variable that measures the distance to the outer horizon. That's the rough intuition. What I want to stress is that when you do that in a near-extremal black hole, it has to be near-extremal, that's the content of the theorem. So if I do the expansion of this two-dimensional subspace of the metric and I apply that large diffeo, what you will obtain is this metric in the new tilde variables. But that metric is locally ADS2. So in a very natural way, we have one statistical mechanics argument saying that near-extremal physics is controlled by very low excitations. And if I try to mimic and focus on the low energy excitations in some gravity setup, it seems that I am instructed to take this lambda going to zero limit in this change of variables, and then the physics is controlled by ADS2 physics. What I want to stress is that this delta energy here, which is linear with lambda, is the same kind of limit that I took in order to keep the partition function finite in my earlier discussion. So somehow, because I have not made any conjecture or anything, this seems to suggest, perhaps not mathematically, but physically, that the physics of a small energies above extremality is somehow related to ADS2 physics. But that has always been the picture. Now, please, of course.
So this your result here gives you ADS2 in a particular coordinate system.
Yes.
Is the statement then, having identified that the physics, the near-extremal physics is related to ADS2, can I then, I mean, how much coordinate independent freedom do I have? You know, so having identified that here's ADS2 in these coordinates, can I then pick another set of coordinates, deduce something from it? Is this gauge invariant physics? Is this coordinate invariant physics?
That's a good question. I'm not sure I have a fully satisfactory answer for you, but I definitely can. I definitely can say, and this is part of the Schwarzschild story, is that, for instance, if we pay attention to this transformation, t tilde equals to t divided by lambda, if instead of using t, I use any other function of t, that is trying to capture the diffeomorphism invariance at the level of the ADS2, if you want to. The argument still goes through, and that changes of coordinates has to do with the asymptotic symmetry of ADS2. So I don't have a full answer, you know, I don't have a yes or no answer, but in the modern perspective offered by, you know, Stanford, Maldacena and company of this near ADS2, a la Polchinski and Almeri, the reparametrizations of the boundary of ADS2 are physical. And I very much believe that this is related to the answer to your question, if I would understand this better.
Right, okay, cool, thanks.
Yeah, no, thanks for asking, a very good question. So maybe the reason I was going so slowly, apologies, on these statements is because I did think about this when I was younger. And the older I get, you know, perhaps sometimes I like to stress to young people that one can be confused for many years. And indeed, this slide is an attempt at connecting the confusions when some of us were younger with the statements that some of you younger people may have read in recent years. So the first part of the slide is trying to summarize very, very broadly and very biasedly how we were thinking about this and why we were confused. Among many things, I would say that we were confused about two things about this ADS2. We knew that if we added energy in a space-time which was asymptotically ADS2, that energy was destroying the boundary conditions of ADS2. That's typically referred to a work by Maldacena, Michelson, and Strominger. And so the meaning of ADS CFT for ADS2 was very unclear because apparently you cannot support matter, for instance, in that setup. Personally, another thing that I always found very confusing, and these days has been used for wormhole purposes, is the fact that ADS2 was known to be the only ADS space to have two boundaries, but they are connected through the bulk. So even though Maldacena understood the story of eternal black holes, the ADS2 remain a little bit of a confusing, to say the least. And then on top of that, the group led by Strominger in Harvard, formulated the so-called Kerr CFT. I forgot here to mention Sen's work. I apologize for that. But basically, the idea behind Kerr CFT is that if you take into account the first bullet point here, you don't want to include excitations because ADS2 boundary conditions get broken. So if you go to my statistical mechanics argument, you only keep the degeneracy of the vacuum in that partition function. And Kerr CFT defines some boundary conditions in gravity in such a way that you are only keeping the excitations of the value of the vacuum. Kerr CFT computes in some setups. It computes using asymptotic symmetry groups or CFT data the degeneracy of this vacuum, just as Sen was also able to do it. So that was the story. But then, even prior to the more recent developments, Almeri and Polchinski asked an extremely natural question, which has been hidden in my arguments. But it takes people that really understand what's going on to ask the right question. So if you view ADS2 as the near horizon of another geometry, this means that tautologically, that even though we know from Maldacena, Michelson, and Strominger that if we add excitations, ADS2 boundary conditions are broken, we already know how to glue the ADS2 throat to some other asymptotics. And in these asymptotics, you may have extra excitations. So this coined the notion of near ADS2, and the way in which I would like to start asking you to think about it is, when we took the near horizon limit, I was asking you to take R to be the outer horizon plus some small perturbation. Let's call this small perturbation a dynamical field. That will be the JT mode in the rest of the talk. And I will do some perturbative expansion by requiring that, strictly speaking, the absolute value of this guy is much smaller than the size of the horizon. This, together with a dimensional reduction, meaning if you start in 4 dimensions, you reduce on the 2 sphere, for instance, allowed Almeri and Polchinski to derive from the Einstein-Hilbert action, like the one that I'm using here as a toy model, to derive some 2D effective action, which is the Jacques-Teitelbaum. So what they wanted to argue in this early paper is that the low energy that I've been trying to advocate using different arguments is controlled by JT gravity, but this ADS2 throat is connected to the rest of the universe, and black hole, near-extremal black holes are evidence for that. Now, what is this JT gravity? Sorry, I realize that probably Jeff will have talked about this for many times in your group, so perhaps I will go very fast. Just to set some notation, I guess. So here I'm reminding you of, this is 2D gravity model with some dilaton coupling. The first line, which is written in terms of phi naught, which is the analog of the R plus in my previous slide. Sorry for the slide change of notation. It's topological in nature, and if you evaluate it, it gives rise to the extremal black hole size or the entropy. The second line is the one that depends on the fluctuations, what I have called the JT mode. And this is bullet 2. This dynamical field is what measures the deviations from the overall black hole perspective, the deviations in the size of the black hole. The JT equations of motion, as you can see here, because of the linear dependence, force the curvature in 2 dimensions to be negative. So that gives rise to this ADS2 metric. If I write it in Poincaré coordinates, this is related to Jeff's question. This is just a local writing in terms of Poincaré coordinates. But at this point, I could have written it in any coordinate system because this is just a covariant equation. And importantly, Einstein's equations provide a constraint for the JT mode. And I will be referring to this set of equations as the JT equations. Now, in these Poincaré coordinates, the general solution in ADS2 for these equations is written here in terms of T and Z in Poincaré coordinates, and they depend on 3 parameters, alpha, beta, and gamma. Now, what is crucial in this story is the insight, one of the many insights in the Maldacena Stanford Young paper, which is how to build the gluing of the ADS2 that we have been discussing and that Polchinski discussed from the perspective of the asymptotic of whatever black hole you started with. In this picture, I am assuming it's Kerr, but the discussion is more general. The idea is that you put some cutoff at what you would call the boundary. Let me go back. This ADS2 in Poincare coordinates has a boundary at Z going to 0. So the size goes to infinity. So what I mean by cutoff is when I am infinitely far away in the ADS direction, I'm probing the inner horizon, the deep inside of the external black hole geometry. So from the ADS2 perspective, it's natural to declare that the metric evaluated at this cutoff surface looks like this. And you are interested in parametrizing this cutoff surface together with providing some Dirichlet boundary condition for the JT field that controls the deviations of the size. This JT field also blows up from the perspective of ADS2, and this is the choice of boundary conditions, which tries to describe basically how you are embedding this red circle. There are fluctuations. It depends on the clock. This is related to Jeff's question, actually. It's parametrizing the freedom that you have in parametrizing this red circle. Okay, so if I denote the boundary time, again, this is Jeff's question, by U, the first boundary condition that these authors solve, this depends on the derivative of T with respect to this clock and the derivative of Z with respect to this clock. You can solve that boundary condition always by this first statement here. And when you use this information to solve for the boundary condition for the JT mode, which is this one here, that relates the source of the matter field, which is the renormalized value of the matter field in terms of the curve T of U. That's the data that characterizes the effective action a la Maldacena, Stanford and company. And when you plug this into the JT action, including boundary terms, they are very important, what you get is, you get an effective action of this form in which I'm trying to highlight with colors two different objects. The source, which is the boundary condition for the scalar field, and the boundary function T of U, this red function. Now, this curly bracket is the Schwarzian, and the insight is that you can view the equations of motion, so that the T of U has to satisfy as coming from the variation in terms of this source. Now, much of the excitement in this story has been that everything I've told you is in the gravity side, but as you know, there has been a microscopic story in terms of some free fermions. I will not go through this because it will not be important. I don't have any insights here for Kerr, sadly. But just to remind you that the connection here is that there is a microscopic model involving some disorder in these couplings of these fermions, such that the infrared limit, so the low energy limit of this microscopic model shares the same symmetry breaking pattern as the one that you observe in JT gravity. So there is a new duality, if you want to. And here I just had some brief derivation for this. But yeah, the lesson to take home is that there is a microscopic model, and the low energy in this so-called SYK model provides a dual formulation of JT gravity. Now, what I also want to convey is that we want to believe that this Goldstone, that this symmetry breaking pattern is always true in near-extremal physics. And so I'm going to be asking what happens for near-extremal Kerr in particular. if you have not seen this, you could ask, well, the standard example in ADS-CFT is ADS3-CFT2, for good or for bad. Some people love it, some people hate it. In this story, you start with 3D gravity, negative cosmological constant with this boundary term. And you dimensionally reduce this 3D metric in terms of a 2D metric, a dilaton that tells me the size of the S1, that's the S1 direction, and some gauge field. That's a standard Kaluza line reduction, but in 3D. And if you do it, that's the 3-dimensional action written in terms of 2-dimensional variables. And here I'm reminding you of the previous boundary conditions. This is the length of the thermal circle. This is the Dirichlet boundary condition for the size of the S1, the same one as before. And I need to provide you with a boundary condition for the gauge field, and that's this holonomy condition. So it turns out that there are some technicalities here that I can rewrite that model in terms of this effective action, which is a gravity model in 2 dimensions coupled to a scalar field in the presence of a non-trivial potential. So that's an example of a two-dimensional gravity plus dilaton field. And if you expand, if you look for solutions in this model around ADS2, which is a solution where the potential satisfies these conditions here, that's what I would call the self-dual orbifold, but that's the near horizon of extremal BTZ. And if you look for perturbations around this, perturbations meaning I look for linear perturbations in some units, which is Newton's constant in 3 dimensions, around the extremal solution, which is just near extremal ADS2, the action that determines the dynamics of these corrections is precisely JT gravity. So that's reproducing the statement that I've tried to solve to you in general for the case of BTZ. And it's very natural to ask, can I reproduce this in the CFT? And it's nice to see that the answer is yes. This will link with the previous statistical mechanics statement. I start with a 2-dimensional Euclidean CFT at finite temperature. This is my Euclidean manifold. These are the beta and the theta chemical potentials that I introduced before. And this is the famous partition function into the CFT. Taking the extremal limit in this case means this first bullet. So I need large C in order to do holography. Near extremality requires beta left and beta right to scale with C in this way. And the claim by the authors that I have not mentioned, but let me stress it here. This is taken from Ghosh, Maxfield, and Turiazzi. The claim is that when you evaluate this partition function in some slightly different ensemble, apologies for not explaining that, you get the contribution from the extremal piece, that's the black part. And the corrections due to near extremality are captured by a partition function, which is extractable from the UV-CFT partition function. And this reproduces the calculations in JT gravity or in the Schwarzschild effective action. So you have managed to understand this in a setup that we have a lot of technical control. And well, I guess that some people feel satisfied about that. Some other people would just say that this is large C. So you decide in which camp you want to be. Now, finally, I want to start discussing Kerr. And in case that you need to be reminded, this is the metric of Kerr, 4 dimensions. So no string theory, no nothing in Boyer-Lindquist coordinates. I will refer to Kerr, full Kerr metric coordinates, typically with tildes. Hopefully I didn't make any mistake about that. So the function that determines the horizon is this delta. You can see that there is the inner horizon and the outer horizon. I'm using the same notation as before. And these inner and outer horizons are related to the mass of the black hole and the angular momentum by this relation here. Near extremality in this parameterization means that the spin parameter, which is this A label, in order not to have singularities or closed term-like curves in this geometry, A has to be bounded between -m and +m. So near extremality means that you reach one of these bounds, and I'm going to be studying A going to M. Now, from our previous discussions, it's very natural to say, hey, near extremality and low energy seems to require to take a near horizon limit. Let's take this near horizon limit, same notation as before. Notice that I'm rescaling the time as before. I am exploring the geometry close to the near horizon, outer horizon R plus, with the lambda going to 0 and modulo signs. This is the same kind of linear transformation in the rotation direction. But in Kerr, spherical symmetry is broken. So when we take this limit, I want to stress that in brown, we still have the ADS2 as before. We still have this, like in BTZ, something like that looks like d phi, which is the fiber where I was rotating. And I have some electric field here. So this is like in BTZ. But the breaking of spherical symmetry means that I have some non-trivial warping factors. So even though the structure of ADS2 is here, even though I have a gauge field here, it's not obvious what is the JT mode, even though I guess that a lot of people in the field would say that all the arguments by Maldacena et al. Should go through in here. So what I would like to do in the remaining part of the talk is to try to explain to you how we manage to answer satisfactorily, how to identify the JT mode. And it's relatively technical, but I hope that the problem has been well defined, at least from a logical point of view. Now I will try to define it more technically for you. And here is my attempt. So what are we going to do? So the thing that we did is that JT captures the fluctuations of the near horizon of whatever extremal black hole you started with. So it seems natural to take, sorry, I forgot to mention, I apologize because I'm too old and for me this is known, but this near horizon geometry for near extremal Kerr has a name. We typically call it NEG, which stands for near horizon extremal Kerr because of our amazing imagination. So I will be referring to NEG, sorry, okay. So that NEG plays the same role as the local ADS2 geometry in the first part of the talk. So JT is describing the fluctuations of a perturbation. Let's call this perturbation this brown H. And so it was natural for us to say, well, before starting with the full battle in full Kerr, which is asymptotically flat, let's try to understand fluctuations, linear perturbations in NEG. Now, as I stressed very early on, and for those that may have considered or studied these problems in the past, it's a huge success in physics, in my opinion, the fact that we were able to, that the community many years ago was able to derive a full gauge invariant treatment of linear perturbations in full Kerr. It doesn't have to be extremal. This was extended to NEG perturbations, in fact. But it's great to have this formalism, and it's gauge invariant, which is a great thing, meaning that you can use whatever coordinate systems you want. Now, the JT mode that you may want to identify, or the JT mode equations that I wrote down before, they, from the perspective of full Kerr, they may have been written in a particular gauge. And I want to mention this route at the beginning because this will be the case. So if you don't get the JT mode on your nose, it may be just a matter of a gauge. And so we don't need to despair, but we need to keep this in mind. And of course, we need to deal with the fact that the spherical symmetry is broken. Now, before we started this project, I think that everyone would have told us, yes, the answer has to be that there is a JT mode here. But as far as we knew, there was no specific identification of this mode in the literature. And the literature is huge because it's not just our community, but the GR community has analyzed perturbations in near-extremal Kerr, even for gravitational wave physics. So our strategy, sorry, I should have gone more to the point, is I'm going to accept that to begin with, I'm going to pick some specific gauge. in order to describe fluctuations for age. And I will do as much as I can to identify all the possible perturbations in this age and to relate them to gauge invariant quantities such as the Weyl scalars that appear in the Tchaikovsky formulation. And from that guidance, I will try to identify what the JT mode is, and then I will perform the gluing if I have time at the end of the talk. But if I don't talk about the gluing, I think I'm fine. So what I want to describe to you is the type of perturbation H. Sorry, I just noticed that I've changed the color. Here is in brown. Here it appears in blue, so apologies. But notice that I am starting with the initial neck geometry, which is written fully in black. This G here is ADS2 in whatever coordinate system you want, and this is the gauge field in ADS2 in any coordinate system you want. This is related to Jeff's question. Now, the perturbations is a specific set of perturbations that don't carry any, that don't break this U1 invariant. So I will refer to them as axisymmetric. They are not the most general ones in that sense. And what you can show by computing the linear equations of motion is that the linear correction to this gauge field, which I have denoted by this curly A, is completely determined, meaning that it is sourced by this scalar perturbation that I will denote by chi. This chi is a function of the ADS2 coordinates, but also of theta. Remember that the problem is spherically broken, and I'm only keeping the U1 invariance. The equation of motion satisfied by this chi is given by this. I don't have a covariant way of writing this, but I hope that you agree that if this statement is correct, we can do separation of variables. And the good news, and perhaps I should have stressed this before, is that in the near horizon that I took here, I didn't write it down, but I should have said, so apologies, we didn't scale theta. So it's actually rather natural that the perturbations in neck will be controlled by equations of motion, which are more or less analogous to the ones in full Kerr. And this will turn out to be very useful. So that's what I'm trying to do here. These are the perturbations in neck, but when I do separation of variables, I introduce some functions of theta, I introduce some functions of ADS2, I will label them by this integer L. And the reason I know that this is an integer L is because of technically, when I write down the differential equation satisfied by this S of theta, it actually satisfies the associated Legendre polynomial equations, which are related to the Kerr perturbation in theta. This is known in the GR literature. So that was good. And it's important to keep in mind that this L starts at 2. I will come back to this in 2-3 minutes. Okay, what about the ADS2 perturbations? The good news is that after separation of variables, you have introduced this separation of variables L, which is quantized. This gives rise to a mass term in ADS2, and you get an ADS2 wave equation. So you get a tower of ADS2 modes. And since L is larger or equal than 2, the delta that you would use in ADS-CFT, Witten's formula, would be L plus 1, so it's greater or equal than 3. Now, all these modes are normalizable. These are the modes that people have found in GR, actually, and we wanted to check, so this is not a new result, I should stress this, but we were reproducing this in our formalism. That's the way I should have phrased it. So these normalizable modes can indeed be put, even though this was in our gauge, in one-to-one correspondence with the ingoing or outgoing modes in the Tchaikovsky formulation. And one way to try to convince you, even though this is relatively technical, so I will not be self-contained here, is that in the Tchaikovsky formulation, the fluctuations of Kerr or neck are written in terms of Weyl scalars, as you may know. The Weyl scalars are diff invariant, so I can compute them in any gauge. If I compute them in the gauge where I perform these calculations here, I obtain this result. I am highlighting the dependence in theta, and I'm highlighting the dependence in the ADS2 coordinates. This requires this contraction with the Neumann-Penrose tetrads, which I have not introduced, apologies, but this is computable. This is a first order in our perturbation, and something very similar occurs for psi4. My remarks are that for the subsector of axis symmetric perturbations, these associated Legendre polynomials capture exactly the same perturbations as people in the Tchaikovsky formulation. So in the Tchaikovsky formulation, you start with psi0 or psi4. That's this psi. You do separation of variables in the master Tchaikovsky equation, and you have some theta dependence. That theta dependence for m equals 0 satisfies the same equation as in our gauge. That shouldn't be surprising because theta has not been rescaled. What is more interesting is that the ULs that appear in my notation here, at least, in this gauge invariant formulation, they do appear like these factors here. And that's what we check, that they contain. There is a one-to-one map. You can invert, you can go from our formulation to the Tchaikovsky formulation. So message to take home is, so far, we are able to reproduce all the normalizable perturbations. But where is the JT mode? Well, the JT mode is not here. So the search continues. Now, if you come from, well, since we've been told, and I personally believe at that point of the project, that there should be a JT mode, I should be looking for something else. Let me try to give you a slightly different argument. If you are a slightly younger person and you are coming from ADS-CFT, if I give you ADS2, one of the things you may ask is, what are the bounds on the mass of scalar fields in ADS2 coming from the so-called Brayton-Lohner-Friedman bound? And what you discover is that that bound applied to ADS2 allows you for L equals 0 and L equals 1. But let me remind you that these modes are not among the normalizable ones. So it makes sense that we didn't find them, but it's natural to ask whether the JT mode is among these ones. Now, technically speaking, the differential equation that this mode satisfy, you can write it down. This is in our paper and in previous literature. You can write it down for L equals 1 and L equals 0. The reason why it's not considered in the standard GR literature is a very good reason, as you can imagine. It's because these modes are not normalizable on the two-sphere. This is a Sturm-Liouville problem. I can give you an inner product, and these guys are not normalizable with that inner product. If you are more physically oriented, perhaps another way of reaching this conclusion is that when you solve these equations for L equals 1 and 0, you see that the solution blows up. It has conical-like singularities, either at the North Pole or at the South Pole of the two-sphere in Kerr. This is quite explicit because of some denominators blowing up. But perhaps the more physical way of saying what I'm saying is that if you would be interested in gravitational wave physics, for instance, these perturbations carry an infinite amount of energy flux. So that's another way of reflecting that they are not normalizable. So these solutions are basically typically thrown away. Now, when we realize this, and I don't have a better way of justifying this, so let me just make the technical realization that we had at that time. We thought, okay, so these modes exist mathematically, but they have this divergent physical behavior. What about trying to keep them by requiring that the energy flux vanishes? This may sound like a very strong requirement, but remember that because of separation of variables, if this L is singular, if I require my ADS2 function, this differential operator to vanish, even if this diverges, the flux will be 0. So that's one natural possible way out of keeping these divergences into the game. I will discuss the singularities later, of course. But to highlight that apparently we were in the right track, let me stress that when we did this for L equals 1, let me be very precise now. I take the non-normalizable L equals 1 modes and I require the Weyl scalars to vanish. These Weyl scalars provide these differential equations for chi. When you combine these two constraints together with the wave equation in ADS2, this is all the data that I've given you so far. These are these conditions here. If you massage these equations, the space of solutions to these equations can be shown to be in one-to-one correspondence with the solutions of what we started this talk with, which is the JT equations. So it seems that we are in track. If we play the same game with L equals 0, we get a 0 mode, which is a constant scalar field. Now, we are not done because we have a connection between vanishing flux and JT equations, but our neck perturbations are still singular. I told you that these S of theta are definitely singular. So it cannot be one of the JT modes. And here is where my previous remark gives some hint as to how we may solve this puzzle, which is we may be working in a gauge where these perturbations are singular, but I may be able to consider a singular diffeomorphism that cancels this singularity. I don't know whether you find this plausible or not, but that's what we did, and that's what I will try to convince you that it works. So let me jump in because time is flying. This is a very important, it's technical, but this is how we managed to solve this problem. The idea is the following. I'm giving you a perturbation in some gauge, which whose dynamical equation of motion is related to JT, but it's written so far, it's written in a gauge in which it's manifestly singular. So you would like to consider a diffeo that is also singular, such that when I combine the previous perturbation plus the diffeo, I get something that is smooth, and that will be the JT mode. How do I come up with a diffeo that is physical and singular at the same time? So the idea that we had is the following. Imagine that you consider a diffeo generated by this vector field. It depends on the ADS2 coordinates, theta, and also the U1 phi. If I consider a vector field that has non-trivial dependence in phi, since phi is periodic, this vector field will generate some perturbations which will typically not be single valued. In particular, if we consider something that is linear in phi times some arbitrary vector field on ADS2 and theta, this is enough to generate something that is non-single valued. And the effect that these diffeos have, if you have ever tried to do this, typically these diffeos, even in flat space, they will generate some conical-like singularity for you. These transformations are physical. They change your metric. Okay, so that's what we were aiming for. So that's our starting point. Now, we wanted the perturbation that is the Lie derivative of the neck metric along this diffeo. That's what this parenthesis is. We wanted the perturbation to remain axisymmetric. So this means that in terms of Killing equations, that the metric should be independent of phi. There is no inconsistency between the vector field being linear in phi and the metric perturbation being axisymmetric. And in fact, what you can show is that if my vector field is linear in phi and I require the perturbation to be axisymmetric, this is equivalent to requiring this blue vector field to be Killing. But now it's Killing only in ADS2 and theta. How do these Killing vector fields look like? And this is actually, so something that I was very happy with. So if I take metrics, let me check time. Yeah, I will try to conclude. If I consider metrics which involve neck in particular, the result is a little bit more general. Please notice the ADS2 piece in here. Please notice the U1 here, the gauge field. But what I claim by the result being more general is that this capital lambda and this capital gamma could be arbitrary functions of theta. They don't have to be the ones associated with neck. But of course, I'm doing this for neck. The claim is that the most general vector field, Killing vector field of a metric of this sort, which includes neck, looks as follows. It has a complicated expression, which I'm not going to try to justify. But what is important is that it depends on a scalar field in red, which I have called capital phi zeta. And this capital phi of zeta actually is a solution of the JT equations of motion in the first place and the zero mode of the JT equations of motion. Most probably I have not highlighted how important this is, but that's the claim. There is a scalar field which is not dynamical that satisfies the same JT equations of motion. And if I plug it into this formula, it generates a vector field that generates a singular V field. To make the story short, what I'm going to do now, please focus on this equation here. That's all that I need. What is the game that I've been playing? I started with neck, which is near horizon extremal Kerr. I consider a perturbation. I have identified the quantum numbers of the perturbation that know about JT, but it's a singular perturbation. I am adding the perturbation generated by this singular D field, that's this piece, and I'm going to tune that piece. Tuning that piece means choosing this red scalar field. I'm going to choose it in such a way that the overall perturbation is smooth. And this can be achieved. And the claim is that this is achieved when our perturbation is this is our chi perturbation at the beginning of the second part of the talk, is equal to the scalar field phi JT and this zero mode that appears, that controls the global symmetry. Okay. So in the remaining minutes, I can tell you some very quickly. This is the main message, though. I can tell you some extra checks that we did in order to confirm that our interpretation was correct, in our opinion. The first check was to compute the Eyer-Wald charges, and then we tried to glue this to full Kerr. Probably I will not discuss two, or maybe I will just highlight the outcome. So using covariant phase space methods, in particular the Eyer-Wald charges, given some close codimension to surface Carly C in general relativity, if I can associate a charge to a Killing vector psi. This is in general, and I'm giving you the expression for this integrand. So one thing that we can do is apply this formula and compute it for the diffuse generating symmetries for our perturbations. Now remember that our perturbations before applying our trick were singular. So when we computed the charges with only with the perturbation, the singular perturbation, what we obtain is that these charges, these delta Qs, were not conserved. In particular, I can show you what we obtain. For the normalizable ones, these charges are zero, so there is no problem. But for L equals 1 and L equals 0, remember, these are neck perturbations. I should have stressed singular ones. When I computed these charges, I don't get a constant. I get an object that depends on the position on ADS2. And the same is true for L equals 0. If I compute the charges associated with this piece, which is the singular diffeomorphism, this is to convince you that these things are physical. I get charges and they are not conserved. This is what I get. And the claim, if we are right, is that if we tune the two contributions to be related by this box, I should get a conserved charge. And that's precisely what happened for us. When I consider this choice, which is the remainder of the previous box, I do get that our perturbations have 4 charges. This is what you would expect because neck is invariant under SL2. These are these 3 charges here. and it's invariant under U1 rotations. This is where the zero mode lies. So we were satisfied with this. Now concerning the gluing, this is very technical and it involves the normalizable one, so let me not bother you with that. What I definitely wanted to stress, in case that you know one of the many Wall theorems that are in the literature, I will stress what this Wall theorem says. And if you don't know it, it may be worth for you to know. So before starting this project, we knew of a very beautiful theorem by Wald claiming that all perturbations to Kerr, full Kerr, which are smooth, have to be either a mass perturbation of Kerr or an angular momentum perturbation of Kerr. I'm trying to highlight in my formula what each piece stands for. This is a mass perturbation in Kerr. This is an angular momentum in Kerr. And then you may have an arbitrary a small diffeomorphism. So this is a diffeomorphism, but it has to be smooth. Now, what we showed in our paper is that in the lambda going to zero limit, which is this near horizon limit, our smooth perturbations in neck do glue to variations in the mass and the variations in the angular momentum. So our result is consistent with Wald. Let me remind you that the Wald theorem is a theorem for the full Kerr geometry, not for neck. So what one in principle has to be careful, and that's what we try to do. There are a bunch of technical results which I decided not to include, but I wanted to stress, in case some of you have some intuition, that there is a funny sector here, because we did realize, model our mistakes. I'm just going to report our current state of mind, that looking at this formula, I could consider perturbations in full Kerr which don't have any mass deformation or any angular momentum deformation. That's what I'm saying here. But I'm considering a diffeo in full Kerr. So from the perspective of full Kerr, this is just a change of coordinates, let's say. And it's a small diffeo, so it's non-physical. But you can actually, if this diffeo would have a non-trivial dependence with the radial coordinate, when we take the near horizon limit, which is this lambda going to zero limit, your diffeo could have some divergent behavior. And actually our analysis is powerful enough to include such possibility. And what we learn is that technically it is possible to have a diffeo, a Kerr diffeo, which is not a Kerr diffeo in neck. It's a physical transformation. It will not carry mass and angular momentum. That's consistent with the gluing, but it can generate two of the other charges in neck. So for some time, I was considering whether there may be a relation between this statement and all these statements by Strominger, Hawking about asymptotic symmetries in near horizons. But I don't have anything clever to say, but this is a technical statement. You can have Kerr diffeos, which when taking the limit, they don't behave as diffeos for neck. Somehow I find this amusing, but this is just a technical remark. And in case that you were going to ask, Wald's theorem is very stringent because he was only interested in smooth perturbations. But there are famous perturbations written in textbooks even of Kerr, which are singular. And our analysis reproduces those. So it's nice to see that that's the case. So let me just highlight that and I finish with this. If I consider one of our singular L equals 0, remember that all the new game was in L equals 0 and L equals 1. If I consider singular L equals 0 perturbations with vanishing Bailey scalars, so they don't have infinite energy flux, but they are still singular. I don't try to cure the singularity. I reproduce the tau naught perturbations of Kerr and the symmetric perturbation, deformation. So I was actually quite happy with this because we seem to recover everything that is known. And just to highlight that our understanding is not good enough, I don't know if our singular perturbations in L equals 0 and L equals 1 are physical. So as soon as the flux is infinite, this doesn't seem to be physical to me. But in case that you are interested, for reasons that I don't fully, well, I understand technically, but I don't know what it means conceptually. This is a hugely technical remark, so apologies, but in case that you have read about these things, the Hertz potential that allows you to reconstruct the perturbation in Kerr is non-separable for these guys. And there is not that much literature, believe it or not, on non-separable Hertz potentials. But again, since I don't know if these are physical or not, so just a summary, I've tried to review some of the motivation, perhaps it took too long, behind near-extremal black hole physics, the fact that the low energy dynamics is captured by by the JT modes in general, and how they have this microscopic connection with SYK or 2D CFTs in the case of a BTC black hole. I've tried to convey a little bit of the logic that we use in this very technical project. I think the question was clear. I can give you Kerr. I can adjust the parameters to have near-extremal Kerr. The arguments by Joan and company would suggest that there is a JT mode, but the spherical symmetry is gone. Where is it? So we were able to identify it in this apparently no, in these non-normalizable modes. But if you require the extra condition that the energy flux of these modes is 0, you can save these modes by acting with a singular diffeo. I feel that there has to be a better way of presenting the result, but at least we have identified the JT mode. There should be a way to phrase this in terms of Goldstone modes, for instance. And another thing that I wanted to, more for GR-oriented people, is that our claims and our gluing with full Kerr, fortunately for us, reproduces the well-known results by Wald. So it seems that hopefully we didn't forget anything. And I just leave this with 2 natural open questions, which I have to say, I don't have any good idea on how to pursue them. But I think I've gone over time, so I'll stop here. Thank you very much for your attention.
Thank you very much, Joan. Any questions? If not, I have a couple. So let me see if I understand the overall philosophy here.
Yeah, please. Yeah, this is important. Yeah.
So the statement is, if I start off with Kerr and I take the near horizon limit of Kerr, then I get ADS2. Right. Yeah. And I guess the philosophy is similar to what we would do to get ADS5, for example, right? You start off with a bunch of D branes, you stack them up, you take the near horizon limit, you make them coincident, they get heavy enough to deform the geometry, you take the near horizon limit of that, and you're getting ADS5, and then you identify the ADS5 due to be the field theory that lives on the world volume of the D branes. Right. So that's the game, that's the overall game that you're playing, except you're doing it with the realistic geometry of Kerr.
Yes.
Right. And you're saying, well, okay, so Kerr has. Actually, I meant to ask another question. Let me slip it in quickly.
Please.
Maybe I missed something. You're taking the near horizon limit of one of the horizons, right?
Yeah, the outer one. Sorry. Yes. I'm trying to go there.
What do you get if you take the limit of the other horizon?
The answer is that I don't know. In the near-extremal limit, since R plus and R minus differ by lambda terms, I would get the same thing. But in general, I don't know. Yeah.
Okay. Cool. But in any case, you're interested in the near horizon near-extremal limit, right? So the horizons get very small.
The horizons are you can see it in this square root here.
Yeah.
In the extremal limit, these two guys are the difference is linear in lambda. Yeah.
Okay. So
but in general, yeah, you're right. Yeah.
Cool. So then you're taking the near horizon limit of Kerr, and you're identifying an ADS2 space-time from this. And given that, you know, the ADS2 is a solution of JT gravity, the natural association is that this becomes JT gravity in some sense. But the point, I guess, you're making is that locally all solutions of JT gravity are diffeomorphic to ADS2, but of course it's the dilaton in the couplet in the multiplet that allows you to have different solutions, right?
Yes.
And that's what you're looking for. What do you identify from the?
Yeah, so I'm looking forward to identify this Goldstone mode, even though my dimensional reduction involves an integral over the two sphere where spherical symmetry has actually been broken. So I have actually integrated. You see this metric here. Yeah. The size of the ADS2 is warped, so it depends on theta. Yeah. So when you actually try to get the JT gravity in 2 dimensions, you have to integrate over the sphere, literally. In the spherically symmetric cases, this just gives you the volume of the 2 sphere, and it relates the Newton's constant in 4 dimensions, say, with the Newton's constant in 2. But here there is non-trivial geometry, which I don't have anything clever to say, but technically I do want to stress that to derive JT is still in 2 dimensions, in the ADS 2 dimensions. Yeah. So we need to integrate over theta. Right. And the perturbations that we did, notice that they have a non-trivial theta profile. So there is, in terms of what you need to do to an SYK-like model, someone needs to understand how to encode this spherical symmetry breaking. Maybe this is a red herring, but yeah. Yeah. Otherwise, we did exactly what you did, what you said, Jeff. We took a near horizon, but please notice that this ADS2 in brown here has this warping factor, and the same with the S1. The S1 has a non-trivial size also. Right. So that's the part that I don't know how to encode microscopically, but it has to play a role. So coming back to your brain picture, Jeff. And I know that what I'm going to say is blah, 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 but this is perhaps, I apologize for being so obscure here. I'm not going to sign an agreement with any of the people that are working out there, but as you said, I'm considering a Kerr black hole in an asymptotically 4-dimensional space-time. I don't know what is the UV description for this theory. Now, let's assume that there is one. I know that this is a big assumption, but as theories, we definitely, hopefully, we agree that hopefully one day a brilliant young colleague will come up with a huge insight. So here, what I've said is that personally, I feel that this may be a BMS invariant dual theory. I don't know if you agree or not, but it's not important. There is some UV theory that describes flat holography. Call it celestial sphere, call it whatever you want. The claim that I would definitely make out of this talk, and I don't think that this is controversial, in my opinion, I'm just rephrasing what you were saying, is that whatever that UV theory is, if I consider the near-extremal limit which captures the fluctuations on top of a near-extremal Kerr black hole, that UV theory has SYK-like physics or JT gravity physics at low energy. That's the claim that I believe that we would all make. Yeah. But I don't know the UV theory, of course. Right. What I know is that, I know what Einstein told us, which is that as an effective theory, this theory in 4 dimensions is described by by general relativity coupled to some matter. That I know. And then from that perspective, we can go back to the early part of my talk and apply the near-extremal and do the reduction. But microscopically, I don't have anything more to say. But the statistical mechanics argument, I believe it's universal. If there is a UV theory, this JT mode that we identified, the JT gravity that Juan also used, should also control the near-extremal perturbations of flat holography.
Right.
But of course, it's useless because I don't know flat holography. So, yeah.
Right.
I don't know if this is what you were having in mind, but I wanted to link your picture of the branes and the decoupling limit or the near horizon limit. That's my UV interpretation of that decoupling limit.
Right. I guess my interest in this comes from trying to understand the lambda going to cosmological constant lambda going to zero limit of JT.
Yeah.
So there's a non-trivial limit to take there to get PGHS basically.
Yes.
But not in the language of CGHS. There's an equivalent formulation by Jakiev and one of his students, Kangemi. They wrote a couple of papers on this. So basically, you have to rescale lambda before sending it to zero, which gives you a central extension of the Poincare algebra.
Okay.
That's the symmetry group controlling the flat space limit of JT. I guess in 2019, I asked Edward if he thought this was a useful thing to do. In particular, the question is, there's all this understanding of JT gravity arising as some averaging over some ensemble, right? And it's because the ADS2 symmetry group and the DS2 symmetry group are the same in 2 dimensions. I don't see that there's an obstacle to doing the same thing for DS2.
Yes. Okay.
Right? But then in between these two, you have this set of measure zero flat space kind of limit between the two, and I don't understand how to understand that as some kind of averaging. In particular, what are you averaging over? What's the ensemble there? But whatever it is, this is flat space. This is zero. This is vanishing cosmological constant, and the corresponding action for that theory would be phi times r minus 2.
Yeah.
Right. So not phi multiplying the whole thing, right? So that's just a phi r minus 2. And so when you vary with respect to phi, that's r equals 0.
Yes.
And the cosmological constant enters that theory as an integration constant, essentially. So in that sense, it's somewhat like Weinberg's modular gravity, where the cosmological constant is not really a constant. It enters as an integration constant for the Ray-Choudhury equations. And so, I was trying to understand if there's some way to see that theory emerge in the same kind of way as what you've described from JT. I mean, from Kerr, but I don't understand that at this point.
Yeah,
I'll send you a link to Jakiev's papers
okay.
on the topic. In fact, I don't know if you have his book. What's it called? Diverse Topics in Mathematical Physics or something like that. In one of the chapters, he has a whole chapter on linear gravity, and part of it is AD, part of it is JT, and the other part is this flat space linear gravity.
I see. So yeah, I mean, right now I don't have any comment except for the fact that since even though our black hole is asymptotically flat, the black hole is near extremal. So the near horizon has negative cosmological constant. So it is natural to get the JT gravity that we are used to. So from that perspective, I feel that you are asking a slightly different question, but I think that I understand a little bit the good motivation that you have. You would like to understand. I mean, JT has given us a lot of mileage, and you would like to try to understand whether you can
get similar mileage from the
exactly. And yeah, if Jacques has made some technical progress on that front, I guess that you would be interested in trying to see how to embed that story in higher dimensional physics, let's say.
Yeah, I guess the lesson to be learned from this is that you should always read Jacques' papers.
Yeah, yes.
I
mean, I think
decades ahead of their time.
Yeah. I think when I say similar remarks to local students in Edinburgh, they probably just think, well, Joan is getting old and he has nothing better. He has nothing more useful to say. But my experience is that great physicists in the past and also right now, of course, whenever they thought about something, what in many cases, as you are pointing out now about Jacques, whatever they wrote down, it may sooner or later be useful. These are great minds.
That's right. I mean, there are a couple of people like that. I mean, where you pick up a paper of theirs, just periodically,
yeah,
and you read it, and there's this new insight. I find a couple, like every time I pick up Tony Z's QFT book.
Yeah. Oh, that's wonderful.
It's a little bit like that, right? I mean, the first time
yes,
the first time I encountered that book was in the early 2000s, and there was so much in it. But as a starting student, you kind of get fixated on some things, and then now you go back to this book and you open it, and he's got pages on replica theory, and he's got sections on disorder. He's got sections on amplitudes. All of these things were set down already in the early 2000s.
Yes.
And then we kind of reinvent the wheel every time we go around this side.
I'm completely on your side. Yeah.
Like you see Clifford's work on JT.
Oh yes.
Right. These are all things that he was thinking of as a PhD student, right? So he's working on the C=1 model and these integrable systems in the context of 2D string theory for a long, long time. And then it just takes one trigger, and suddenly you realize that actually all of this stuff is what people are interested in again. And so, but you have like years and years of background on this. So it's really fascinating to kind of see these ideas crop up again and again and again. And then there are a couple of these really great physicists that if you just go back and read their papers, and they're these gems of ideas that clearly they like Polyakov's book is another just you pick it up every now and then, and you realize that we're just going around in these big circles and rediscovering these ideas that were had by these guys.
Polyakov is an amazing example.
I find for me that I guess the two are Polyakov and Jacques, and it's just every time I go read one of their papers, you realize that these ideas were remarkable for their time. And so now the converse is you should read the papers that they're writing now. Jacques is writing papers on graphene at the moment, on like chiral gauge theories for graphene, and you're like, I bet in a couple of years this thing will be what everybody's working on.
That's right.
Anyway, it was fun catching up. Thank you for the excellent talk.
Thanks for the invitation. Anytime. Yeah.
And it will be wonderful to see you in person again. Um,